Okay, so we're on air. So today's speaker is Silvester from the University of Manchester, and he's going to give a talk about efficient linear algebra and uncertainty quantification.
So to start with, I want to just say what a delight it is to be here in Cambridge giving a talk. As we heard, so these seminars, I went to one last week, actually. It was 2 hours long. And I'm a bit conscious about time, personally. I wouldn't say I'm OCD, but I'm probably on the spectrum. So I think I don't want this talk to be over long, for sure. So my kind of thinking process was to keep it snappy. So you can see that it's quite an open-ended title. And in terms of keeping it snappy, I might have overdone it. So what do we do now? Clearly the answer is yes, okay, so that's for sure. Linear algebra is going to be important in the bit of uncertainty quantification that I do. The talk is in 2 pieces. I'll time myself, or I can see a clock there. I'll spend maybe 30 minutes or so on the first piece. Some of you in the audience have heard bits of this before from other speakers, including Catherine. So that's the kind of the main bit of the talk. Depending on how time goes, I'll talk about a different thing. They're both involving linear algebra and the differences in the application that I'm talking about. So part 1 is about a model problem, a linear PDE model, elasticity. Part 2 is a non-linear model, more complicated, but the uncertainty comes into it in an easier way, as we'll see. Okay, so if this works, you can see part 1. Okay, so the work I'm talking about, as I say, is joint work with other people, and 2 of these people are actually in the room. That's Catherine and Alex, and Arbaz was here maybe about a month ago and gave a talk on a similar topic, but would almost certainly have said almost nothing about linear algebra. So it's essentially the same talk, but with a different emphasis. So we've got an episode project, and essentially I'm reporting on what's been achieved in the first year of this project. We're interested in PDEs with random data and designing efficient approximation methods for solving such PDEs. So the focus of the talk is exclusively on this methodology called stochastic Galerkin, and the reason we're using this is that it enables an adaptive process which has some rigorous underpinning. It's not an ad hoc process, there's some rigor behind it, but the stochastic Galerkin approximation method comes with a linear algebra overhead. So this is referred to generically using this horrible term of intrusive, as opposed to a sampling method, which is labeled non-intrusive. So intrusive is a word I really despise in this context. I don't know who coined it. To me, it sounds like you've got some invader in your house or something. It's something that's got bad connotations, and there's nothing bad about an intrusive method. And the reason there's nothing bad about it is that the thing to be afraid of is the linear algebra, and I'm going to show you that we can deal with the linear algebra. That's the motivation for kind of everything that we're doing here. So this is just part 1, as I say, which I think will take about 30 minutes. These are the aspects I'm going to talk about. I've got a nice big stick here I'm going to just point to. So 4 things. So there's very limited finite elements expertise in the room here, I understand that. So I just want to say some things about mixed approximation in a finite element context, try and explain to you why that aspect is important. The focus is on elasticity equations, and elasticity equation, the formulation we're using, is a multi-field problem with a constraint, and this is where mixed approximations are used. My background's in fluid mechanics, and the elasticity equations are very similar to a model in fluid mechanics of very slow flow called the Stokes equations. So I just want to talk about that. Then, of course, we're in a UQ themed program here. So where's the UQ? Well, the most important thing I believe in this elasticity context is this Young's modulus. This is the modulus of elasticity of the body we're deforming, and we want to model this as not as a deterministic thing, but as a random thing. We don't really know the elasticity modulus or the Young's modulus everywhere in the body, but we've got good information about, say, a mean value, and we're going to have some statistical model of the perturbations. I want to say something about functional analysis. That's not the focus here. That was more of a focus in Arbaz's talk. And then linear algebra, where does it play a role? And can I link these things together? Because this functional analysis here is going to be very closely related to linear algebra, as we'll see. And it doesn't look like a standard linear algebra talk where you talk about matrices and think about matrix algebra. This is a more PDE-oriented approach where the linear algebra is kind of bespoke. The linear algebra methods I'm talking about will only work for this application. They won't work in other ones, as we'll see. There's two papers you could look at if you want to see some background. They're both on archive. The most important one is the second one. That was submitted in January. And indeed, yesterday we got referee reports. And they didn't recommend rejection, so that gives me a little bit of confidence that everything's okay here. So it's been submitted to CISC. I'm pretty confident it'll be accepted this time round. So maybe within about 6 months there'll be actually a paper on this topic. And it's directly related to what I'm saying here. You can get it from archive. And just to say something about software, I really believe in reproducible research. And for me, it's very important that when I'm generating results, that you have confidence in my results. And so if you want to generate these results yourself, you can. All the software is available. Okay. I would like to see everybody adopt this strategy, whereby you want to reproduce somebody's results, you can run their software and get the same results. So that's the case here. The software is written in MATLAB, but it runs, the IFIS software is actually quite a big package. It's been developed over a period of 15 years. There's like 600 MATLAB functions, many thousand lines of code in this package. And we have a special kind of add-on, which we call SIFIS, is when you've got some uncertainty in the problem. Okay, so here's the model problem. So this is linear elasticity, and I'm going to start at the bottom and work my way to the top and try to describe this problem to you. It's a non-standard formulation of elasticity. I call this the Herman formulation. And the reason it's non-standard is it's designed to be robust. In a sense, I'm going to explain now. So
Elasticity has got material parameters in it and material things. The key thing is we want to load somebody, not a person, sorry, something, some plate. Okay, so we're going to do things in 2 dimensions. Of course, real life elasticity is the 3D body. Probably the most important thing in structural engineering is this problem. You stress a body, a bridge for example, or a plane's wing, does it break? So F is the loading term, and U is the displacement under that load. P here sits around, has no real role, it's an auxiliary variable, and doesn't appear in standard formulations of elasticity. So P has got the name, the Herman pressure. So Herman is the name of a person who came up with the ideas are quite old, I would say. But anyway, so we've got the displacement U, and the displacement term is related to tensors, and there are 2 tensors knocking around. First one is rate of strain tensor, which would be a 2 by 2 matrix. So this is the symmetric part of the gradient matrix. That's epsilon here. And then the strain is related to the stress by this relationship. So mu appears in here, which is one of the material parameters. And there's a second parameter here, lambda, which normally what you would do is you'd substitute P in here. So the stress would be related to the rate of strain and the divergence of the U, the displacement. So in a normal formulation, you don't have this substitution of P, you
you just substitute this in here, so this reads as 2 mu epsilon plus lambda divergence of u. That's a normal formulation. And then you substitute this into the first equation, you have like one vector valued equation. It's a standard elasticity model. But this model caters for aspects of compressibility. So that's, I've highlighted that in red here. So nu here is a material parameter. It's called the Poisson ratio. It depends on the material that you're compressing. So some materials are more compressible than others. Metals typically have a compressibility of about 0.3. They live between 0 and 0.5. 0.5 actually isn't achievable, but some things are very close to 0.5. Rubber is a good example. Compressibility, the Poisson ratio for rubber is 0.4999 to 4 decimal places. That's very close to a half. And if you look at this parameter lambda, then as nu tends to a half, this blows up. Lambda goes to infinity. So this is the problem with incompressible media. The standard formulation of elasticity breaks down. Okay, so you can't have nu too close to a half, otherwise lambda goes to infinity, and that means that sigma blows up as well. So it means you get arbitrarily large stresses from relatively small loads, for example. So this formulation is designed to be robust in the limit. You can actually, the way we set it up, you can actually set nu equal to a half, and the formulation is still valid. Because as lambda goes to infinity, this term drops out, and you're left with essentially a simpler problem to solve. But you have two equations knocking around. You have an equation, the price of paying by having robustness is you've got an additional equation. So we've taken our elliptic equation, if you like, and we've added a constraint. So I'm interested in this model.
So there's no materials for nu is close to 0?
Yeah, there is. I was actually looking this up. Cork is 0, which is why it's used in wine bottles. It makes it easy to pull it out when you...
Don't you get into trouble with that formulation when nu is 0?
Oh, I hadn't thought about that. Can I come back to that? Yeah, okay. Right, okay. I was only thinking about the other limit.
Yeah, no, it's fair, that's fair.
Okay, so as I say, we're modeling uncertainty here. So what I haven't said so far is where is the uncertainty? So E is the thing that's going to be uncertain. That's the modulus of elasticity. And the uncertainty is parameterized by a vector y. So this is a vector of parameters. And we're going to be in this setting whereby, in principle, this is an infinite dimensional vector. Okay, so which we'll explain in a moment. Okay, so y blue, that's the color coding, means parameters. Okay, so of course coming from Manchester, red and blue have special connotations, and one of these colors is obviously a better choice than the other, but we won't actually get there. Okay, but anyway, blue is parameters. Red are very important things, as in Manchester. The red team obviously is much more important than the blue one.
Can I just say about Max's point, if nu was well away from a half, I don't think you'd use this formulation. There'd be no benefit in using this formulation if nu was well away from a half.
Here's my model for the uncertainty in the Young's modulus. I'm modeling it as parameter-free part. Think about this as being the mean part. With this, we're going to set this up so these things have mean value 0. So we'll think of this as being the mean part, and in the applications or the examples I'm going to show you, this is a constant. Okay, so the mean part, this is the material parameter. And we've got perturbations about mean with some given functions, ekx, which is spatial, and these parameters which take values are going to take values between -1 and 1. They're going to be images of uniform random variables. I don't want to belabor this point too much, but you want to set things up so that your PDE is well posed. There exists a solution that's unique and is stable with respect to changes in the data. So this is a sufficient assumption which gives you that. And it's assumption on E. You want to be bounded away from 0, away from infinity, at every point in space, and for all possible values of y. This is a sufficient condition, and in terms of what we're going to do, we have a stronger condition that we're going to have. Typically, we're going to insist that we're going to have that this is constant, so this is positive, so this is automatically satisfied. This is about how fast this sum converges. We want this
sum to converge nicely, so we're going to insist on, relative to the mean, so we're going to insist on this condition here, where this sum is bounded away from 1. That's going to be an important consideration. So as long as we satisfy this, we have this, and the preconditioning, the linear algebra stuff I'm going to talk about, is all going to work well. Okay, so I'm trying to think, when we actually met for the first time, we kind of decided this was going to be the first problem we solved on our project about a year ago. And I can't remember exactly how the conversation went with Catherine, but we kind of figured out pretty quickly that we've got a problem here. And the problem is with the formulation, because E, remember, is random. It's parameterized anyway. And we've got an E in here, inside this equation, because it's defined. E is sitting in the in this equation because mu is directly proportional to E, and there's a mu sitting in here, so sigma depends linearly on E. But then we've got a lambda here, and lambda's got lambda's E, so 1 over lambda is 1 over E, so we've got a non-linear dependence on the parameters. So we've got kind of like proportional here, inversely proportional here. What do we do in terms of modeling this? And there's a very simple idea that opens the door to simplicity here, and that is to introduce another variable, yet another pressure. So we call this the modified pressure, where we rescale the Hermann pressure by dividing by E. So this parameter here, when we do this gives us this relationship, and this thing here, the lambda thing in red, this is parameter free. So we've got a new pressure which depends on the divergence of the displacement, which is parameter free. So when you write down what you've got, you now have what we call the three-field formulation. In 2 dimensions, this is 2 equations. So we've got 4 equations, 4 PDEs to solve with this structure. And these lambda hat things, they are independent of the parameters. And in particular, this equation here, for P tilde, there's no parameters in it. The parameters are down here. But if you look at this equation, now there's no parameters in this, so now all the uncertainty is in the 1-1 block of these matrices. It's here, there's an E here, and there's an E in here, so we don't have this inverse dependence on E now. Very simple idea, which is very clever. So we only have to model E, we don't have to model the inverse of E as well. We're going to set this up with standard boundary conditions engineers use. So this means that the body, whatever it is, let's call it a plate from now on, the plate has got prescribed displacement, so you fix the plate, for example, when G is 0 on some bits of the boundary, and this is the 0 normal stress condition, which means it's just hanging kind of in the atmosphere, as it were. Okay, so that's the setup. I thought I had too few slides, and now I'm beginning to think maybe I'm not going to actually achieve my objective in finishing in 30 minutes. But let's press on. I'm not going to spend too long on this slide. This is the functional analysis part. So to define our elements on this model, we need appropriate function spaces, test space, solution spaces. We need to figure out what they are. This is relatively standard stuff actually for people in the know. And just in terms of the parameters, that might be the most interesting part. So that these spaces H1, L2 have got a standard. But this space here, this bottom space, is just to think about the parametric dependence. Basically, it's the least squares norm. So we're kind of looking for parameters in some sense which have finite second moment, finite variance. It's going to be the assumption that we have on our parameterization, or the random variables underlying the parameters that are there. Okay, so this is the weak formulation of the same problem. It's a 3-field problem, as you can see. It's conventional to write down these things with standard bilinear form, so let's just look at the structure of this. So you want to write this down as a symmetric system. So A is a symmetric bilinear form, B is not, and C and D are both symmetric bilinear forms. So you just want to get the signs of these things set up so you reflect the symmetry in the problem. So A is reflecting, this is like the standard elasticity formulation with the parameters in front, E. B is a weak version of the divergence operator. C is the thing which is parameter free. That just involves the pressure and the test function pressure, the L2 version of that. And we've got another bilinear form D, which has got the parameters in it, the same kind of thing, but weighted by E. So again, it's just nu here is the important thing. Remember, nu can be, let's say, 0.3 or 0.5. As for those choices, alpha doesn't change very much. But beta, of course, does change in this limit. So beta can be infinite when the Poisson ratio is a half. And in that limit, this term drops out and this term drops out. And the formulation simplifies in the way I said already. We just have a two-field formulation now, which looks like a Stokes problem. Okay, so this next slide doesn't look so important, but this is really the key to the whole talk, I would say. So what one wants to do now is come up with some way of measuring the energy, I'll call it the energy, in the system. And you want to get scaling done correctly with respect to these parameters. Remember, alpha and beta depend on the material parameters. And by doing the functional analysis and working with it, you figure out the correct norms and the correct scalings. So this is the L2 norm of the gradient of the displacement, L2 norms of this is the Hermann pressure, and this is the modified pressure that we've introduced. And with these scalings, you can show well-posedness. So that means if F is bounded, small changes in F, you're going to get small changes in the solution. That's what we want. And the parameters in front of alpha minus a half is a very benign thing. Alpha is just something like 1. So what we see here is an E min and a C, which depends on E max. So the important thing is, the thing we've got here is like E max over E min, which is the variation in the input.
Sorry, so just to explain parameter dependent, alpha and beta, they depend on the Poisson ratio, but they don't depend on any of the input parameters, the random parameters.
Right.
They only depend on mu, on the Poisson ratio.
So they don't, sorry, they are got different type of parameters now. Let's call these material parameters. Okay, they're not affected by changes in E. These material only depends on mu. Nu in the way we've done it is fixed. We're not changing the Poisson ratio, keeping that fixed. Okay. Is that the end of that? Yeah. So this norm is going to be the key, as I say. Okay, as we'll see. I don't want to spend too long on this because this is kind of for the experts. So we want to do Galerkin approximation. So that means we take finite dimensional subspaces of the displacement space, that's going to be called VH, finite dimensional subspaces of the pressure spaces, there's two of them, but it's the same space, L2, we'll call that WH, a scalar field, this is a vector valued field, and for this all to work, we're in the business of mixed finite elements, and there's this famous compatibility issue, it's got names of people associated with it, Radishenshire, Bushka Betsy, you might have heard of this. Max is like a local expert and some aspects of this. We need to ensure this stability condition, which means that this space has to be chosen to be compatible with this space. You can't just arbitrarily mix your approximations of displacement and pressures, you've got to do it carefully. This has been well researched though, so compatible pairs are well known. I started in this business as a PhD student in the 1980s, and literally when I started, there was only one stable pair of approximation spaces which were known to work, but over time, more sets of stable approximations have been developed. So this is called the Untitled condition. Think of that as compatibility condition between this and this constant here, gamma, the Untitled constant, as it's called, will play a role later. But the important thing is that this is a positive thing, and it's got to be uniformly bounded. So that means not for any mesh, not for any discretization, this isn't zero. It's got to be bounded away from zero. So as you refine your mesh, this gamma has to stay away from zero. Otherwise, you're going to run into stability problems. Okay.
Sorry, gamma depends on the parameters.
No. This is just to do with choice. This is the spatial approximation. There's no parameters here. This is the spatial approximation, not the parameter part of the approximation.
When you say stability, you mean stability in some solver you're going to use?
Stability of the solution even, right? You can get arbitrarily wrong solutions by using unstable approximations. It's a big topic. Some methods are very close to being stable and engineers like to use them nonetheless, but there's a bit of danger associated with that. So the good thing to do is to look in the books. There'll be tables of stable pairs. And Max has got a book on this. Look in his book. There it is. This is a stable approximation pair. Just use those. Don't mess with unstable approximations. And I speak for this from a position of, of experience, of having played with unstable approximations. Okay, this is the parametric approximation. So again, I think it's been quite a theme throughout the program now, isn't it, this notation? It was originally introduced by, I think, Gittelson and Schwab for this setting, or maybe Cohen, when you have an infinite set of parameters. So we're going to be working in this setting where this is an index set, so we've got different parameters. So this is going to dimension about how many random variables. This is going to be a high dimensional problem, how many of these we introduce. So for example, this goes up to 10, we've got 10 random variables in our problems. We have a 14-dimensional problem, but this could be 100, and we'll have 100 parameters. We're working in a 104-dimensional space. And this alpha here gives you the index of the monomial in that parameter that you're using. So alpha 1 equal to 2 would mean like quadratic in the first parameter. Alpha 2 equal to 4 would be quartic polynomials. And we use polynomial approximation in these parameter spaces. We're living in a box, a hypercube. So what's done typically, everything is smooth with respect to parameters. We use P approximation. That's global polynomial approximation, which is adapted to the underlying distribution of the parameters, or the things the parameters came from. So that's the Legendre polynomials for uniform random variables. So these things here are the Legendre polynomials. Global Legendre polynomials of increasing degree. So we have this set of finite support, indices of finite support, and then we take subsets of this and we generate approximation spaces which are products of, this is the displacement field. So here's the spatial approximation producted with this set of parameters, and the key thing here is that this is the same as this. So we don't take different spaces for the parameters for the different variables, the displacement and the pressure. And because of that choice, it means that we only have an if-sub condition which is relevant to the spatial parts of the approximation. We don't have to worry about the parameter bits being incompatible because we're using the same things. The Galerkin formulation then is the same as the weak formulation, except it's all in finite dimensions. So that's the same setup, except now this is a finite dimensional object, this is a finite dimensional P, and the test function is a finite dimensional. The system's square, because we're using what I would call Galerkin-Budinov projection. This was the main topic of Arbaz's talk. So this is like now how we would solve a real problem with an increasing number of parameters in an adaptive way. We're going to control the adaptive algorithm using a posteriori error estimation. That means we compute a solution on a given mesh with a certain parameter set. We estimate the error precisely, and this error estimator is going to be called eta. We estimate the error by solving problems of slightly higher dimension. So in space, we refine the grid, and we explore what would happen if we did a grid refinement. And in parameters, we increase the number of random variables, and we explore the impact of increasing the polynomial approximation in the parameters that we've got. So we've got an estimate for the error in this norm, and we've also got tight, I would say, bounds on the error reduction. That's what's happening here, which would be achieved in the first case. We're starting from an approximation which is on a given mesh H with a given parameter set, whatever that is, lambda. And this is what we would get if we were to do a spatial refinement. We can generate this estimate without doing the spatial refinement. We generate an equivalent measure. So this tilde measure means it's up to a constant which doesn't depend on these parameters that we're worried about. So that's coming from this choice of norm up here. So these constants here are not in any sense related to the material constants. So we have a measure of what would happen if we did a spatial refinement, and we can also compute what would happen if we did a parametric extension, that is, increase the number of random variables in our model of E, or increase the polynomial approximation in any component of E. We can compute these numbers and then use this to drive an adaptive refinement process. And we start with something very coarse, we increase the spatial resolution, we increase the number of parameters, we increase the parametric approximation until some tolerance is satisfied. We're reducing the error, and we do this in a rigorous and systematic way. It's not an ad hoc procedure. So just to show you that with kind of a test problem, so we'll take a unit square, we'll take a problem with mixed boundary conditions. We could have a force which is either at 45 degrees to the mesh or horizontal, which is parallel to one of the coordinate axes. We take a model for E. Again, this is a pretty standard model now as a test problem in the literature, whereby the mean is 1, and we've got variations which depend on Fourier modes in each direction, cosines. These are the y-ims, the parameters, which are random numbers between -1 and 1, or images of random numbers. And alpha m are coefficients we want to decay, and you set this up in such a way that the problem is always well posed, and such that you can control how fast this series decays. We're looking for some kind of algebraic decay, and we can fix it with this decay factor sigma. And the two cases of interest that one always uses, I would say, or we use, is sigma's 2, which we call slow decay, and sigma tilde is 4, which is fast decay. So fast decay means these things decay very quickly, so you don't need many of these terms to achieve a certain error tolerance. Remember, this is the uncertainty in the input, and we're trying to see how this affects the output. Okay, so we've got a slow decay and a fast decay case, and the adaptive algorithm then proceeds something like this. So I want to show you the difference between a compressible material 0.4 and something which is very close to incompressible, 49999, close to 0.5. And because of our robust formulation and our well-chosen error measures, there isn't really so much difference between these two approximations. So each of these is a step of our adaptive algorithm. So in this case, we've taken about 10 steps. That's with 0.4. When we did 0.4999, we took more steps. You can't see this very well, but we've solved the problem with about 10 to the 6 degrees of freedom in total. Okay, so we've solved our parametric PD problem on a laptop like this in seconds.
Do you remember how many parameters got activated?
I'll show you that next. So that's the other thing. So you can run the software and you can actually see it. You've got a PD to solve an elasticity problem, and you're solving it in seconds, and in principle there are infinitely many parameters in your model. So in this case, let's just look at how many were activated then. So here's a picture of this is the adaptive step. The yellow ones here are the number of active random variables, which start with just 1. It increases over the course of the calculation. And so for this problem, 0.4, we ended up with 4. And this is the number of active indices that were generated. And in this case, we ended up, 9. Whereas the second problem, run the code, we don't know what the Poisson ratio is, we just want to make sure it's robust, and this time we end up with like 15, between 10 and 20 parameters activated, and an index set between 50 and 60. All automatically generated. And those were the numbers behind these things. So the right-hand side corresponds to this, and the left-hand side corresponds to this. We end up with the same error tolerance. We're stopping in this kind of with the same error reduction in both cases. So the total number of degrees of freedom is slightly bigger here than here, but we're still talking about order 10 to the 6 degrees of freedom. Now, one reason why I can do it on my laptop is that I can solve the linear equations fast. Okay, so if I didn't have the linear algebra, I wouldn't be able to do this. And the people who complain about intrusive, they're kind of like, I hesitate to use the word lazy, but that's probably a good word to describe them, because they can't be bothered to actually invest in the linear algebra. They just want to use the code they've got already. So the alternative to this would be to do some kind of sampling, Monte Carlo sampling. You'd have no rigorous error control. You wouldn't know how many parameters to activate, and you would have difficulty solving the problem, anything like the amount of work that we've used to solve this problem. Just to show you some pictures of, so we have pictures of solutions. So this is just displacements of this body. The displacement itself is tiny, but if you look at something sensitive like the variance, you can see there are differences in the pictures between 0.4 and 0.499. qualitatively they look very different. That's the vertical displacement. More interesting probably is the pressure. This is this artificial variable, but when you look at the pressure, you can see that there are singularities in the pressure, and this is where the Neumann boundary condition meets the Dirichlet boundary condition in the corner, and with the forcing in this direction, so we have a pressure singularity here, and in this case, it's different because it's more compressible, we have two singularities. So the adaptive spatial refinement should deal with this fact that the singularities are in different places. Okay, so that's, I'll pause for a moment. Is everyone happy with, kind of happy where we are? So took a long one, and I'm not going to spend a lot of time talking about linear algebra. I want to just highlight the key issues that I want you to feel comfortable with the idea that this Galerkin approximation, tough linear algebra is okay. You can talk to some people who know what they're doing or read their papers. You're going to be able to do it. You can download their software. It's going to work. Don't be afraid of Galerkin approximation. Okay, so this was the weak formulation. Let's write down bases for these functions and write this down now as a matrix formulation. So how does it look? Okay, so I'm assuming that at the stage we're at, we've activated m parameters, so we have to run over this sum over m of them. We haven't activated the m plus first yet, so we're just making this sum finite, the tractable computation. So we've got this alpha parameter, we've got gk's, these correspond to the Legendre basis functions, and these ak's, these correspond to deterministic finite element approximations of this variable. And you end up with this Kronecker product of these matrices, which is kind of bad news, it's really big. The dimension of this thing is the product of the dimension of this or the dimension of this. So the dimension, the number, the spatial approximation could have 10 to the 4 or 10 to the 5 degrees of freedom. This is the size of the index set, so that could be 10 squared. So that's why we get 10 to the 7 degrees of freedom. So this system, typically the ones we're solving are 10 to the 7 degrees of freedom on a laptop, something like that, in a few seconds. As I say, the intrusive guys worry about that huge dimensional system from their perspective. You cannot do backslash. You can't call any direct solver of any software and apply this system to it. It will run out of memory. Okay, so that's the end of the story. We can solve these systems because we use an iteration method. We don't compute the inverse of this matrix. The iteration method works by computing approximations to the solution doing matrix vector multiplies. So for our iteration method, we have to do a matrix vector multiply with this operator. So we don't need to assemble these big matrices, the Kronecker products. We can do the matrix vector multiply just by knowing what the pieces are. Okay, so this is the coefficient matrix, just my red and blues now again. So parts of this matrix are parameter free, that's this bit, that's the divergence term sitting here and here. Remember, this equation is completely parameter free, so everything is red here. Okay, so G0 is the identity, by the way. So this is the identity, so this is many copies of B1, depending on the dimension of the parameter space or the index set. Whereas here, where do the parameters play a role? They play a role here. So we've got sum over GKs, and down here, this 2-2 block for this, the equation that determines P tilde, the modified pressure. Again, we've got the same thing, but you can see this structure here. So the idea of the linear algebra is to, or the efficient linear algebra, you've got to exploit this structure. Okay, so the first thing you do is you don't have to do this, but in terms of making this thing look more normal, what you would do is you'd commute this matrix, this block and this block. That just means interchange P and P tilde in these equations. It's like just changing, making this equation number 2, this equation number 3. And when you do that, this is the same system, and that is a very characteristic shape because now we've got kind of a big 1-1 block, which is symmetric positive definite. We've got these rectangular blocks. I've got a 0 block down here, and this is a saddle point system. So you can recognize it. Okay, so this matrix has this shape. The matrix is symmetric, and it's indefinite. It's necessarily indefinite by Silvester's law of inertia. If you apply it to this matrix, so it means the eigenvalues are all real, but they live on both sides of the axis. And you can count the number of eigenvalues which are negative. It's the dimension of this space of our modified pressure. That's precisely how many negative eigenvalues you have. So you can't use the simplest methods that are kind of out there. The most simple one is conjugate gradients. This won't work because it's designed for symmetric positive definite system. You have to use a bespoke method. That's MinRes, the minimal residual method. So we're going to solve this using this method called MinRes. It's a short-term recurrence method. It requires a matrix vector multiplier at every step with this matrix K. And to accelerate convergence, if you didn't do anything, the convergence algorithm would be incredibly slow. You need what's called a preconditioner. So I guess Catherine's now told everybody about what preconditioning is, maybe not. So the first preconditioner you might think of using is this one. You keep this matrix here, which is symmetric positive definite. And in here, instead of 0, you compute S, which is the Schur complement. This is what you get by doing Gauss elimination on this 2 by 2 matrix. This is the fill-in, or minus S is the fill-in. So this is called the Schur complement. And if you were to use this as a precondition for this, you could guarantee convergence in 2 iterations. 2, independent of any parameters. So this, as a precondition for this, converges, MinRes converges in at most 2 iterations. But you can't do this because S is a dense matrix. You haven't got A-1 for a start, but anyway, this would be a crazy thing to do. But you have the hope that if you can now design approximations to Cal S, you might have something which is equally good, and that's in fact what we do. So we use a methodology called block diagonal preconditioning. I did it myself. My first breakthrough in scientific computing was in the 1990s to develop this methodology for Stokes equations. And this is quite a natural extension now to this problem with parameters in it, the same methodology. What's just one thing to say about this, the matrix M has to be positive definite. So you're preconditioning in an indefinite system, the matrix, which is the preconditioner, has to be positive definite. So that's slightly strange if you think about the precondition being an approximation to the matrix, because it can't be, because the matrix has got in positive and negative eigenvalues, but your precondition has to have positive ones, so it can't in any sense be an approximation to the original matrix. It isn't. What it does, it clusters the eigenvalues. So you end up with eigenvalues which are clustered on the right-hand side and on the left-hand side, and the optimal clustering would be just having one eigenvalue on the right and one on the left, and there's a finite termination property. That would be your 2 iterations if you were to achieve that. So using the exact S, that's what it does. It gives you an eigenvalue of 1, essentially an eigenvalue of -1, and you get convergence in 2 steps. With this strategy, with approximations, we end up with a cluster on the right-hand side, around 1, say, and a cluster on the left-hand side. I'm going to show you some results in a moment. The thing I want to just speed up, because this is maybe too technical for everyone. I think there are 2 really good ideas here. 3, maybe. One was the idea of introducing the 3-field formulation. 2 was the identification of the right norm to do the analysis in. And 3 is coming here, which is how we design our preconditioner. And what we do, and this goes back to work of my own actually, but it's well explained in a paper by Mardell and Winter, 2010. I've got another paper on this thing, is that you identify the blocks of your matrix, your preconditioner, with the terms in your energy. So this block is associated with this term, because this is multiplying the displacement. This block is associated, So these 2 blocks are the displacement, the first component, the second component. This block is associated with this term, which is the modified pressure, and this term here is associated with the Hermann pressure. So you put these blocks on the diagonal. Now to get these norms, you should have sums in blue things, but now you want to make this cheap, so you replace the sums of blue things by red things, which means you use the mean. So that means that this preconditioner will be relatively straightforward to affect the action of the inverse of, because we really just need, this is many copies of stiffness matrix. The deterministic problem, it's the mean stiffness matrix. This is many copies of the stiffness matrix again. This is a mass matrix, many copies, and this is a mass matrix. So we can affect the action of the preconditioner very effectively, very fast, and we don't have, it's independent of the number of random variables in the problem, we're going to lose something in the process, but we're going to retain what's called spectral equivalence of the norm, which I'll say in a moment. So that's also a clever thing, okay, to come up with that motivation. You wouldn't guess that that's the right thing to do, unless you knew a lot of the theory behind this. So I don't really want to spend too much time justifying it. We can prove some relatively small theorems about how good this approximation is. So SDI is the thing I just said. It's approximating this very dense matrix S, and this is a statement of how close the approximation is. It's spectrally equivalent to it. The only things that appear in the equivalence are the subconstant, which we talked about. This is the match between the two spaces. Typically, this might be something like 0.2 gamma squared. That's what that number is, about 0.2 for a square domain. It depends on the topology of the domain, but not on the size of the domain. So for a square, let's say that's 0.2. This is 2. E0 max and E0 min. I said that I was going to keep the parameter free part constant, so those are both 1. So this is a bound between 0.2 and 2. So all the eigenvalues, this is a Rayleigh quotient. This tells that all the eigenvalues remain bounded between 0.2 and 2, independently of all the parameters that you have, independently of the spatial mesh, independently of how many variables you've activated, the polynomial approximation. You're guaranteed this approximation. That means that your solve is going to be really fast. You can take that and actually write down bounds for the eigenvalues from these results. Here's bound. This is the negative side. This is the positive side. The numbers here are just, this is 0.2. This is 2, and U min and U max are, I didn't say too much about this, but we're going to approximate this 2 by 2 block also by a diagonal block, and there's an approximation there, and so that's also spectrally equivalent with parameters U min and U max. They depend on things like the Korn constant. I'm not going to get into where they come from, but those are numbers also close to 1. So let's just look then at, I could wrap up very quickly now, I'm thinking about that. So let's just look at one example, just to kind of like convince you that this is going to work. This is, in some sense, a hard problem, or a harder problem. So here's a representation of these, completely cooked up, it's completely artificial. I blame Gannon and Spanos for this. So you end up with an approximation which is associated with a covariance function in space, and it's this L1 covariance function, which is very rough actually. So 2 is the correlation length, and it's not very smooth because there's no 2 here, it's just to the power 1. We have this definition of the covariance. We compute eigenvalues and eigenfunctions of this operator. These are the eigenvalues, these are the eigenfunctions, so it looks like a KL expansion. We truncate after m things, and we're not doing adaptivity here, we're just going to take m parameters, and we're going to take polynomials of total degree p, let's say 4 in these parameters, which will be a large dimensional system. Q2p minus 1 is a stable finite element pair, biquadratic displacement, discontinuous linear pressures. That's not so important, doesn't say that that's a stable approximation. And let's see how it goes. What can we do? And here's some numbers. So one of the beauties of our min-res algorithm, kind of like a side benefit of this, is that when you're running min-res, you're running an associated what's called a Lanchos process, which gives you information about the eigenvalues of the matrix. So these numbers are not bounds. These numbers are computed on the fly when we're solving the problem. Using min-res, we can estimate the eigenvalues, extremal eigenvalues, and they're tight inner estimates of the eigenvalues. So we have bounds, so this is actually what happens. We run, this is 2 different grids. This is a uniform refinement in space of this grid. We take m is 5, 8 and 10. We want to see how things change as we increase the number of random variables. We fix p to be 3, but the situation, it's not going to depend on p actually. And then we're looking to see whether these things stay bounded. So one thing then to note is if we go from here to here, this is a spatial refinement, there are 4 times as many eigenvalues here. It's a spatial refinement. Dimension's gone up by 4, everything else has stayed fixed. But the eigenvalue, where the eigenvalues live, is essentially the same. So you increase the dimension of the problem by 4, but you've got a spectral interval, your eigenvalue is going to stay in there. That means with the same number of min-res steps to solve that problem. if we change the, this case turns out to be easier, this is the compressible case, because when we go to the close to incompressible case, then this number here is about the same, the leftmost eigenvalue, and the right interval looks pretty similar. So the number that changes is this one. That's the most positive negative eigenvalue. You can see that this is about 0.3, this is about 0.17, it gets closer to 0. But it stays bounded. It's not going to get any closer as we make this close to 0.5. So with this interval, min-res is going to take more steps than with this interval. But as we change the number of parameters, as we change the grid, it's not going to grow. Okay, and so I don't know where these timings were. This was on somebody's laptops, I think. Arbaz's laptop to actually solve a problem. Okay, so this is showing the robustness with respect to the Poisson ratio. This is the number of iterations to solve to a certain tolerance. 10 to the minus 6 is a pretty tight tolerance for doing the linear algebra. And what we see are bounded iteration counts, bounded times. And the thing to, again, to observe is like, in this setting, it's the spatial refinement that's going to hurt you. As you refine the mesh, you're going to introduce many more degrees of freedom. So this is a uniform refinement. So there's 4 times as many degrees of freedom, let's say going from here to here. The number of iterations is the same, and the time, 7 seconds, goes to 25 seconds. So that's linear in the number of unknowns. So the time taken to solve the problem is just proportional to the number of unknowns in the problem, which you could never achieve in a direct solver for sure, unless it's a diagonal system or something. So you may or may not be impressed by that. I think I'm impressed by that, but I guess I would be. But I think you might be impressed by it if you actually ran the software and you could see how fast you could solve these problems. I don't think I would.
Equations it is overall to give somebody, so like you said, it's solved in a couple of seconds, but
I can't remember. I think they were of the order 10 to the 6, something like that. Million equations to be solved in like 6 seconds. It's not just that we're solving large dimensional systems, we're solving the right large dimensional systems because of this adaptive selection of the parameters. This is a set of parameters which is going to minimize the energy. It's going to give us the most value for money, if you want to call it that. So what have we achieved? I don't want to spend, I'm not going to do part 2, which is about Navier-Stokes equations. We've had enough here. It's the same story, but it's now in a fluid dynamics context. Again, what I wanted to make the point was that don't be afraid of the linear algebra. You want to solve these parameter-dependent problems with structured uncertainty. Galerkin approximation is a great way to go. And so here, as I say, 3 ideas that are good. The 3-field formulations, really simple idea that makes a big difference. The adaptive algorithms also a very important idea for the whole process to make sense. This Galerkin approximation and this robust preconditioning so the linear algebra works. This part here, so I say it's almost like an afterthought. People generally working in approximation theory, if you've got this sense in this meeting, tend to ignore the linear algebra by and large. Told by Catherine, she whispered it in my ear. Statisticians often seem to ignore the linear algebra.
I did not say that. I did not say that.
I thought you whispered it. Yeah, I misheard what you said. But we take it seriously. I think it's important, and so I think that'll do. So thank you for all listening to that.
Any questions, comments?
So you have these codes on link or just inputs and outputs?
The whole code is there.
Oh, okay.
Not actually, so we kind of have a rule of, I don't know how to say it, a rule of submission. We don't give the codes away to everybody until the paper's accepted.
We hold it to ransom until the reference.
Until that point in time, you kind of have to pay the author's money, as it were, if you really want to see it. But I'm hoping that within 2 months, so the code is there, but not this linear elasticity
Yeah.
stuff isn't there. Okay.
Fair enough.
Do you believe that it's a good idea to have code of this type, which is reproducible?
If I wrote good code, yes.
You
You write good code.
You
yes.
have to be confident, right?
Yeah.
If you're confident, it's a good idea, isn't it?
Oh, absolutely.
Intrusive versus non-intrusive, anybody want to? So I
So
hope
you're ready to
everybody,
write another intrusive versus a non-intrusive paper?
Am I ready to write one?
Or Howie's ready to write another one? I mean, because this, when, that paper didn't have this much, this kind of stuff in it, did
I don't think so. I mean,
it? Yeah, the comparison of intrusive.
I think Matthias is the guy that was really also somebody, Herman is somebody who would make the same argument.
Yeah,
I think it's the argument's really done from a point of ignorance. That people
absolutely.
are actually just afraid of the, and I've seen this also for in another context before I did this parameterized stuff. It was true for Navier-Stokes equations. These uncoupled methods were taken because people only want to solve symmetric positive definite systems, and they were afraid of indefinite systems. So it's a historical thing that people don't trust linear algebra unless it's provided in some kind of nice black box. And direct solvers, sparse direct solvers, the backslash in MATLAB is fantastic. There's no two ways about it. You don't even have to think about it. It solves the problem quickly almost all of the time until you get to a problem like this. And then you do have to think about it. And that's a question of whether you're lazy or whether you're not. Is there a better word than lazy? I don't know how to say it. People will say they just got better things to do with their time or something. I don't know what the word is for that.
Maybe ignorant.
Sorry.
Maybe ignorant.
So how much tailoring does it take to take this idea and apply it to some different set of differential equations? I've just got no concept.
Okay.
As a naive statistician, of just
Fine.
how much is
That's a good
required
question.
and how
Okay.
problem specific it is. 'Cause that's one reason people might select a bad, in inverted commas, method. Right? If it's very easy to apply to your problem, then it might be attractive just because you could.
So if you're doing sampling, you'll have a matrix with this structure, but there'll be no G's, and there'll be no crosses. That's what your deterministic code will be. It will be the A's. You have all these matrices, and if you did a three-field formulation, for example, you would have the C's and the D's, and you'd have this without the Kronecker product structure, and you'd have to solve it multiple times with different values of input parameters. Okay. So to take that code and to make it work here, you need code to generate the G's. That's it. So this is pretty simple stuff actually. It's a three-term recurrence for the Legendre polynomials. You need code to generate the G's. Then you need code to do the matrix vector multiply with a matrix of this type. Okay. That's not so difficult to actually do, because you just have to remember that you've got these Kronecker products and do them in the pieces as you're going along. You have an extra loop, in other words. And then you have to, MinRes is built into MATLAB, it's available. Now you have to think about what the preconditioning is. If you take this recipe of working with the norm, that also is automatic. So you have to write something, but all the ingredients are there. And certainly,
But say an even more basic thing is you need to know what your underlying equations are. You, yes, might already have a piece of software that you can stick inputs in that actually is generating all of the matrices that you see on the right-hand side, but you would need by hand to be able to derive that system so you know what else you need to provide in terms of wraparound code. But if you don't know what your underlying equations are, then you wouldn't even be able to write that down. Which is part of the big discussion we've had is about taking other people's code and actually not knowing, not just what the numerical method is, but also what were the continuous equations, what were the PDEs that it was actually being designed to solve. Because if you don't have that information, it's very hard to go from that to there.
it's
But if
definitely
you can sketch that out, if you've had the structure, you can sketch that out as a starting point. Once you've sketched that out, you know what existing code that you have. As David said, everything that's sort of on the right of those Kronecker products. And then as long as you understand how to get those things from the code that you have, it is then relatively straightforward to provide the extra matrices that you have and some wraparound things. But if you don't know how to sketch that out, pretty much, you need to know what your independent equations are.
I mean,
And many people here don't work in that setting.
we were talking to a number of people last week who were using off-the-shelf virtuous commercial codes to do CFD,
Yeah.
and they just couldn't.
Yeah.
They don't have access to this.
They don't have access to
It's a
indices. Yeah. It's a bespoke method. Okay, you have to kind of go back one level away from the way things are. But the payoff is good. I mean, the example I want to point to is Sandia Labs, for example. Sandia Labs do a lot of UNQ. They are designing libraries which enable just this, because they're also moving in this direction, if they can, away from sampling to doing stochastic Galerkin approximations, and they have C++ software to generate all these matrices, to generate these things, to do the matrix vector product, so it's there, it's happening.
So the term intrusive means all this blue stuff.
Yeah.
That's what it is.
And the large dimension. Yes, the blue stuff, they're not there in the original problem.
And then and you have to do it because you're close to a pole, because something's getting very large somewhere in the system. That's something's blowing up, and you need to work close to something which is.
That's just to do with this formulation of elasticity, which is not well. It isn't a stable formulation in this for these materials like rubber.
Right.
So you have to change the formulation if you want to solve such a problem. Typically, engineers use the standard formulation and they just say we're not solving problems which are very incompressible. They'll see things breaking down. You'll see papers in the engineering literature where they'll start taking 0.49, 0.499, and then the results are starting to get screwed up. Not the solver, but their actual results of their simulations. So
It's actually a very good application to illustrate why models should be used with care. Because if you just had a standard model where you could stick in different values of the Poisson ratio, and it didn't actually implement this mixed formulation, you would get garbage. And if you didn't understand that, then, you know, and you just wrapped a sampling method around a standard code, and you just generated, your sampling method generated realizations of your Poisson ratio that were very close to a half, and actually the computer model, as you would call it, was not designed to be robust in that setting, then you would be computing unstable approximations and then doing statistics on top of that. So
I mean, we do have problems in statistics where we also are lazy to deal with. I mean, like with maximum likelihood estimate is close to a boundary, and then we have to use what we call, what's an RB, people like resolution of singularities. So there's a few statisticians who try to develop stuff on these difficult boundary problems. There's not many such statisticians. So it's a good lesson to us to take care.
So how abstract can you make this whole process in theory? I mean, how much structure do you have to assume in the matrix and stuff like that? Can you do a quite abstract theory of including the preconditioning?
you can do it for abstract linear sample point problems. That's what we're talking about here.
Yeah.
That's the winter paper really. So any mixed formulation, electromagnetics, etc., they're all amenable to this. The restriction in terms of what I've shown you is that we've got this affine dependence on the parameters. That's key to it.
Lots of
Some
people.
non-linear dependence on the parameters is a completely different story.
Yeah, that's true for.
Like a
true for
logarithm
everyone.
distribution or something, or whatever it is. So that's the built-in
Yeah.
requirement that we have. Shall I switch the thing off now? Then we can have some real questions.